Hi, well this is my first attempt at a flipped lesson, so let's see what this happens. Okay, we're just going to look at how we can represent waves. And as you can see from the slide here, there are two ways that we can represent waves. This is the Vulcan salute here. Okay, the first is by a displacement time graph. So you'll notice here on the y-axis we've got displacement, here on the x-axis we've got time. Now, remember that this is a graph, this is not a picture of the wave, okay? And in a transverse wave, of course, the displacement is perpendicular to the direction of energy transfer, but of course, in a longitudinal wave, the particles are moving parallel to the direction of energy transfer, okay? So, if we look at this graph here, split it out, the graph here, we can see this length here represents the period of the oscillation of the particles, yeah, the time it takes for one complete oscillation. Okay, and we can remember that, of course, because the unit of the x-axis here is time. Yeah, so this um, distance here actually represents a time. Okay, now it's important to remember, even though this looks like a transverse wave, it could be a transverse wave or longitudinal. Yeah? This displacement here doesn't tell us in what direction the displacement is. Yeah? So this is just a graph. Okay, the other way we can represent a wave is a displacement distance graph. Okay, now you can sort of imagine this is like a snapshot of the wave, but again, the displacement over here, it tells us the displacement at different distances, but it doesn't tell us whether the displacement is parallel or perpendicular. And again, this time, this distance does represent the wavelength, okay? Because in fact, this anything along this x-axis is a distance, so that is the wavelength of the wave. And again, just got to be careful here. Even though it looks like a transverse wave, in fact, this displacement distance graph could be representing either a longitudinal or a transverse wave. Okay, that's it. Okay, now I'm going to talk a little bit about wave intensity. I wonder if any of you can guess, well, first of all, who this group is and why I've decided to use this picture. Okay, wave intensity, definition, defined as the amount of energy per unit time flowing through unit area. Now, if you think about it, energy per unit time is a watt per unit area per meter squared. So a wave intensity is measured in watts per meter squared. So you can sort of visualize what that means. If you imagine if you had a window, yeah, see this window here, let's imagine it's 1 meter squared, so 1 meter by 1 meter. If 1 joule of light energy flows through that window every second, then we can say the light intensity is 1 watt per meter squared. Okay, now what would happen in a lesson here is we go outside and we'd look at a lamp and we'd imagine what would happen to the energy of the lamp as it's spread out from the light source. And of course what happens, I'm going to skip the slide over there, is the energy will be spread over a sphere. And of course we know the area of the sphere is 4 pi d squared, where d is the radius of the sphere. I suppose I should have used r really. I think in the data booklet it's actually a d. Okay, and so if we divide the power of the light source by the surface area of the sphere, we'll get the power per meter squared, which is the intensity. I'll just go back again. Yeah, so the intensity at a distance from a light source is the power of the light source divided by 4 pi d squared, where d is the distance from the light source. Aha, that's why it's d instead of r. Okay, nearly finished actually. Now there is of course a relationship between the intensity of a wave, the amount of energy it carries a second per square meter, and the amplitude. A bigger amplitude is going to be a bigger intensity. But the relationship between the two is a little bit more complex than that. Yeah. In fact, the intensity of a wave is proportional to the square of the amplitude. Of course, don't forget another way of writing that. Instead of the intensity is proportional to the amplitude squared, we can multiply by a constant, and it turns it into an equal sign. So the intensity is equal to some constant that depends on the type of wave times the amplitude squared. What that means, of course, is if we double the amplitude of a wave, the intensity will be 4 times greater. Okay, and there's a little bit of a mathematical proof of that. Yeah, if the intensity equals ka squared, if we double the amplitude to make the amplitude 2a, so now the new intensity is k times 2a squared. Of course, 2a squared is 4a squared. So the new intensity is 4ka squared, which of course is quadruple the original intensity. And of course, surfers know this. They know that if you surf a wave that's 2 meters in amplitude, that it's way more powerful than a wave that's just 1 meter in amplitude. Okay, and there should be a worksheet to go with this. Come and see me if you've got any questions. I think that's the last slide. Oh no, there's some homework, but that doesn't really apply if you're watching this. Okay, thanks very much. First one.